Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
William Kingdon Clifford's On the Space Theory of Matter, presented in 1876 to the Cambridge Philosophical Society, stands as a remarkable, albeit initially speculative, vision in the history of physics. It proposed a radical departure from the Newtonian conception of a passive, Euclidean space, suggesting space itself is active, dynamic, and intrinsically linked to the nature of matter and force. This essay will explore the genesis of Clifford's audacious idea, dissect its core tenets, trace its surprising influence on later scientific developments, primarily in the realm of general relativity, and examine its initial reception alongside subsequent reinterpretations. Clifford's proposal did originate in a vacuum. The mid-19th century witnessed a surge of interest in non-Euclidean geometries, spurred by the independent work of Nikolai Lobachevsky, Janos Bolyai, and Bernard Riemann. Riemann's 1854 habilitation lecture on the hypotheses which lie at the foundations of geometry provided a particularly fertile ground for new ideas. Riemann envisioned space as a manifold, whose geometric properties could vary from point to point, and whose curvature could be influenced by the presence of matter or energy. This contrasted sharply with the prevailing Newtonian view of space as an immutable, absolute backdrop against which physical events unfolded. Clifford, a brilliant mathematician with a keen interest in philosophy and physics, was deeply influenced by Riemann's work. He recognized the profound implications of variable curvature. In particular, he speculated that what physicists perceived as matter and forces were, in actuality, manifestations of the curvature of space itself. He proposed that space was filled with tiny space warps, or regions of non-Euclidean curvature. These warps constituted the fundamental building blocks of On the Space Theory of Matter. Clifford did articulate this idea in precise mathematical terms. Instead, he painted a qualitative picture, a conceptual framework that lacked the rigorous mathematical machinery needed for quantitative predictions. He envisioned these space warps as being incredibly small, far below the limits of experimental detection at the time. He suggested that the interactions between these warps, their motions and distortions, gave rise to the forces we observe in nature, such as gravity and electromagnetism. The very notion of a separate matter residing within space became superfluous matter, became an intrinsic property of space itself. The initial reception of Clifford's space theory of matter was mixed at best. Many physicists found the idea intriguing yet exceedingly speculative. The lack of concrete mathematical formalism rendered it difficult to test or even to evaluate critically. Moreover, the theory offered no immediate advantages over the existing Newtonian framework, which, despite its limitations, had proven remarkably successful in explaining a wide range of physical phenomena. Clifford's ideas appeared more philosophical musings than a viable physical theory. Despite the initial skepticism, Clifford's vision did not fade into obscurity. His concept of space as an active participant in physical phenomena, rather than a passive stage, proved remarkably prescient. Albert Einstein, while developing his theory of general relativity in the early 20th century, acknowledged the influence of Riemann's ideas and, indirectly, Clifford's speculations. General relativity, published in its complete form in 1916, posits that gravity is not a force in the Newtonian sense, but rather a manifestation of the curvature of spacetime, a four-dimensional manifold combining three spatial dimensions with time. Massive objects warp the fabric of spacetime, and it is this curvature that dictates the motion of other objects. In essence, Einstein realized Clifford's vision of matter being intimately linked to the geometry of space. It is crucial to stress the qualification that Clifford's theory was a qualitative precursor, a philosophical inspiration, to Einstein's mathematically rigorous theory. Clifford did possess the necessary mathematical tools to formulate general relativity. He lacked the crucial physical insights and experimental evidence that guided Einstein's work. Einstein was informed by the observed anomalous precession of Mercury's orbit, the experimental results of the Michelson-Morley experiment, and the theoretical framework of special relativity. Clifford's contribution lies in his conceptual leap, in his bold suggestion that space itself is the key to understanding matter and its interactions. He articulated this idea decades before the scientific community possessed the tools to develop it fully. One can point to specific mathematical structures that, while perhaps unknown to Clifford in their full modern form, resonate with his ideas. For example, the study of differential geometry, particularly the work of mathematicians like Tullio Levi-Civita and Gregorio Cicurabastro, provided the mathematical language necessary to describe curved spaces and tensors, mathematical objects which describe physical quantities, independent of coordinate systems. These tools proved indispensable for Einstein in his formulation of general relativity. Furthermore, the concept of a space warp, which Clifford introduced as a qualitative notion, finds a mathematical analogue in the solutions to Einstein's field equations that describe black holes and wormholes. Black holes represent regions of spacetime where the curvature becomes infinite, creating a singularity. Wormholes, hypothetical topological features of spacetime, connect two distant points in the universe through a tunnel of extreme curvature. While Clifford could never have conceived of these objects in their full mathematical detail, his intuitive notion of space warps captures the essence of these exotic phenomena. Moreover, Clifford's work presaged later developments in unified field theories. After the successful formulation of general relativity, Einstein and many other physicists sought to unify gravity with electromagnetism and potentially with the strong and weak nuclear forces into a single comprehensive theory. These attempts, while largely unsuccessful to date, often involve modifying the geometry of spacetime or introducing additional dimensions. Clifford's initial vision of matter and forces arising from the intrinsic properties of space continues to serve as an inspiration for these ambitious endeavors. Of particular note is the possible connection between Clifford algebras and the later development of quantum field theory and string theory. Clifford algebras, named in his honor, provide a mathematical framework for describing objects with both magnitude and direction, objects known as spinors. Spinors play a fundamental role in quantum mechanics, describing the intrinsic angular momentum of elementary particles such as electrons. Moreover, in string theory, elementary particles are represented not as point-like objects but rather as tiny vibrating strings, and the mathematical description of these strings often involves Clifford algebras. The potential link between Clifford's mathematical legacy and Lee's advanced physical theories suggests a deep and perhaps yet fully understood connection between geometry, algebra, and the fundamental laws of nature. The story of Clifford's space theory of matter is compelling. It is a tale of intellectual audacity, a revisionary idea that initially lacked the necessary mathematical armor to conquer the skepticism of the scientific establishment. The story possesses intrigue. It highlights the importance of qualitative thinking and philosophical speculation in the advancement of scientific knowledge. A researcher possesses the freedom to consider any possibility, even the most far-fetched. His work stands as a reminder that progress does involve challenging established paradigms and exploring uncharted territories of thought. Subsequent generations may refine a researcher's ideas, arm them with the tools of mathematics and experiment. The refinement enhances these nascent ideas into concrete theories. Clifford's 1876 work possessed profound influence. The work spurred Einstein and others involved in the theory of general relativity. Clifford's vision serves as an inspiration for physicists pursuing unified field theories and exploring the fundamental nature of space, time, matter, and gravity. It reflects the importance of interdisciplinary thinking, of bridging the gap between mathematics, physics, and philosophy in the quest to understand the. In conclusion, William Kingdon Clifford's on the space theory of matter represents a visionary, if not fully realized, contribution to the history of physics. While it lacked the mathematical rigor and experimental support to be accepted as a complete theory in its time, it planted the seeds for radical ideas that would later blossom in Einstein's general relativity and continue to inspire physicists today. Clifford's legacy resides not merely in the specific details of his proposal, but in his bold and prescient vision of a dynamic, active space as the very foundation of matter and force, a concept that continues to resonate with the ongoing quest to unravel the mysteries of the cosmos.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.